NENOMATICA, where mathematics meets YouTube excellence. Today, we're going to explore an important concept in algebra, the difference between identities and equations. Let's start by understanding what makes an identity special and how it differs from a regular equation. Let's examine these two expressions. Let's analyze the first equation. First, let's expand the left side. 10 times y plus 10 times 1. This simplifies to 10y plus 10. So we have 10y plus 10 equals 10. Subtracting 10 from both sides gives us 10, y equals 0. Dividing both sides by 10, we get y equals 0. This means the first equation is only true when y equals 0. It's a regular equation with a specific solution. Now, let's analyze the second equation. Again, we expand the left side using the distributive property. 10 times y plus 10 times 1. This simplifies to 10y plus 10. So we have 10y plus 10 equals 10y plus 10. Look at that. Both sides are identical. This means the equation is true for any value of y. This brings us to the definition of an identity. Identities are algebraic equations that are true for all possible values of their variables. When we substitute any value for the variables, the identity remains true. The key difference between an identity and a regular equation is that an identity is true for all possible values of its variables, while a regular equation is true only for specific values. In our example, the first equation is a regular equation that's only true when y equals 0, while the second equation is an identity that's true for any value of y. Let's look at some common examples of identities in mathematics. The Pythagorean identity in trigonometry states that sine squared of theta plus cosine squared of theta equals 1. Another common identity is that a minus b squared equals a squared minus 2ab plus b squared. Also, a plus b times a minus b equals a squared minus b squared. You can verify these by substituting any value for the variables. They will always be true. To summarize what we've learned today, you can verify these by substituting any value for the variables. They will always be true. To summarize what we've learned today, an identity is an equation that is true for all possible values of its variables. A regular equation is only true for specific values of its variables. Understanding this distinction is crucial in algebra and helps us solve problems more effectively. Welcome to our mathematics tutorial. Today we're going to learn about verifying mathematical identities by testing specific values. An identity is an equation that is true for all possible values of its variables. To verify if an equation is an identity, we can use different approaches. One simple approach is to test the equation with specific values. Let's understand this concept through some examples. Let's look at our first example. We have the equation x times open parenthesis x minus 1 close parenthesis equals x squared minus x. Let's verify if this is an identity by testing specific values. Let's first understand what this equation is saying. On the left side, we have x multiplied by the expression x minus 1. On the right side, we have x squared minus x. To verify if this is an identity, we'll check if the equation holds true for several values of x. First, let's check for x equals negative 2. If x equals negative 2, then the left side becomes negative 2 times open parenthesis negative 2 minus 1 close parenthesis, which is negative 2 times negative 3, which equals positive 6. The right side becomes negative 2 squared minus negative 2, which is 4 plus 2, which equals 6. Since both sides equal 6, the equation is satisfied for x equals negative 2. Let's try another value. Let's check for x equals negative 1. If x equals negative 1, then the left side becomes negative 1 times open parenthesis negative 1 minus 1 close parenthesis, which is negative 1 times negative 2, which equals positive 2. The right side becomes negative 1 squared minus negative 1, which is 1 plus 1, which equals 2. Both sides equal 2, so the equation is satisfied for x equals negative 1. Let's check one more value. Let's check for x equals 0. If x equals 0, then the left side becomes 0 times open parenthesis 0 minus 1 close parenthesis, which is 0 times negative 1, which equals 0. The right side becomes 0 squared minus 0, which is 0 minus 0, which equals 0. Both sides equal 0, so the equation is satisfied for x equals 0. Let's check one more value. Let's check for x equals 1. If x equals 1, then the left side becomes 1 times open parenthesis 1 minus 1 close parenthesis, which is 1 times 0, which equals 0. The right side becomes 1 squared minus 1, which is 1 minus 1, which equals 0. Both sides equal 0, so the equation is satisfied for x equals 1. Since the equation is satisfied for all the values we tested, it suggests that the equation x times open parenthesis x minus 1 close parenthesis equals x squared minus x is an identity. Let's also verify this algebraically. On the left side, we can expand x times open parenthesis x minus 1 close parenthesis to get x squared minus x. This matches the right side exactly, confirming that this is indeed an identity. Therefore, the equation x times open parenthesis x minus 1 close parenthesis equals x squared minus x is valid for all values of x, making it an identity. Let's look at our second example. We have the equation x squared plus 1 equals 2x. Let's verify if this is an identity by testing specific values. Let's check for x equals negative 2. If x equals negative 2, then the left side becomes negative 2 squared plus 1, which is 4 plus 1, which equals 5. The right side becomes 2 times negative 2, which is negative 4. Since the left side equals 5, and the right side equals negative 4, the equation is not satisfied for x equals negative 2. Let's check for x equals negative 1. If x equals negative 1, then the left side becomes negative 1 squared plus 1, which is 1 plus 1, which equals 2. The right side becomes 2 times negative 1, which is negative 2. Since the left side equals 2 and the right side equals negative 2, the equation is not satisfied for x equals negative 1. Let's check for x equals 0. If x equals 0, then the left side becomes 0 squared plus 1, which is 0 plus 1, which equals 1. The right side becomes 2 times 0, which is 0. Since the left side equals 1 and the right side equals 0, the equation is not satisfied for x equals 0. Let's check for x equals 1. If x equals 1, then the left side becomes 1 squared plus 1, which is 1 plus 1, which equals 2. The right side becomes 2 times 1, which is 2. In this case, both sides equal 2, so the equation is satisfied for x equals 1. Since the equation is not satisfied for multiple values we tested, it's not an identity. It's only true for specific values of x. Let's solve this equation algebraically to find when it's true. If x squared plus 1 equals 2x, then we can rearrange to get x squared minus 2x plus 1 equals 0, which can be factored as open parenthesis x minus 1 close parenthesis squared equals 0. This means the equation is only satisfied when x equals 1. Therefore, the equation x squared plus 1 equals 2x is not an identity. It's only true when x equals 1. Example, let's examine our first equation, x plus x equals 2x. Let's check if this is an identity by testing with different values of x. If x equals 1, then the left side gives us 1 plus 1, which equals 2. The right side gives us 2 times 1, which is also 2. So the equation is true for x equals 1. If x equals 5, then the left side gives us 5 plus 5, which equals 10. The right side gives us 2 times 5, which is also 10. So the equation is true for x equals 5. In fact, this equation is true for any value of x. When we add x to itself, we get the same result as multiplying x by 2. Therefore, x plus x equals 2x is an identity. Fade in, let's analyze our second example. The equation is x plus x equals x squared. Again, let's test this equation with different values of x to see if it's an identity. If x equals 0, then the left side gives us 0 plus 0, which equals 0. The right side gives us 0 squared, which is also 0. So the equation is true for x equals 0. If x equals 2, then the left side gives us 2 plus 2, which equals 4. The right side gives us 2 squared, which is also 4. So the equation is true for x equals 2. But what about x equals 3? The left side gives us 3 plus 3, which equals 6. The right side gives us 3 squared, which is 9. Since 6 is not equal to 9, the equation is not true for x equals 3. Therefore, x plus x equals x squared is not an identity because it's not true for all values of x. It's only true when x equals 0 or x equals 2. Let's understand algebraically why the second equation is only true for specific values. We start with the equation x plus x equals x squared. This can be simplified to 2x equals x squared. Subtracting x squared from both sides, we get 2x minus x squared equals 0. Factoring this expression, we get x times 2 minus x equals 0, which simplifies to x times 1 minus x equals 0. Therefore, either x equals 0 or 1 minus x equals 0, meaning x equals 1. Wait, there's a mistake in my calculation. Let me correct it. Starting again from 2x minus x squared equals 0, we can factor out x to get x times 2 minus x equals 0. This means x times 2x equals 0. Therefore, either x equals 0 or 2 minus x equals 0, meaning x equals 2. So the equation x plus x equals x squared is only true when x equals 0 or x equals 2, which confirms our earlier testing. Let's summarize what we've learned about identities. An identity is an equation that is true for all possible values of the variables involved. We tested two equations, x plus x equals 2x, which is an identity because it's true for all values of x, and x plus x equals x squared, which is not an identity because it's only true for x equals 0 and x equals 2. To determine if an equation is an identity, we can either test various values to see if the equation holds true for all of them, or solve the equation algebraically to find any restrictions on the values. Welcome to our lesson on mathematical identities. Today we'll learn what makes an equation an identity and analyze several examples to understand this important concept in mathematics. First, let's understand what a mathematical identity is. An identity is an equation that is true for all values of the variables for which both sides of the equation are defined. This is different from a regular equation that might only be true for specific values of the variables. Let's look at our first example from the exercise. The equation x to the fourth power minus x squared equals x squared times the quantity x minus 1 times the quantity x plus 1. To verify if this is an identity, we need to check if both sides are equal for all values of x. Let's start by expanding the right side. When we expand x squared times the quantity x minus 1 times the quantity x plus 1, we get x squared times x squared minus 1, which equals x to the fourth minus x squared. Now we can see that the left side, x to the fourth minus x squared, equals the right side, x to the fourth minus x squared. Therefore, this equation is true for all values of x where both sides are defined. It is indeed an identity. Now, let's move on to our second example. The equation 3x plus y equals x plus 3y. Let's rearrange this equation to see if it's an identity. We can move all terms to one side. 3x plus y minus x minus 3, y equals 0. Simplifying, 2x minus 2y equals 0, or 2x equals 2y, which means x equals y. This equation is only true when x equals y, not for all values of x and y. Therefore, it is not an identity. Let's examine our third example, the equation y squared plus 1 equals y. Let's rearrange this equation to standard form. We move all terms to one side. Y squared minus y plus 1 equals 0. This is a quadratic equation. For it to be an identity, it would need to be true for all values of y. However, this quadratic equation only has specific solutions where y satisfies the equation. Therefore, this is not an identity. Now, let's consolidate our understanding of mathematical identities. A mathematical identity is an equation that is true for all values of the variables where both sides are defined. Our examples showed, example 1x to the fourth minus x squared equals x squared times the quantity x minus 1 times the quantity x plus 1. This is an identity. Example 2, 3x plus y equals x plus 3y. This is not an identity, as it's only true when x equals y. Example 3, y squared plus 1 equals y. This is not an identity, as it's only true for specific values of y. To verify if an equation is an identity, we can 1. Transform one side to match the other two. Rearrange to see if it reduces to a tautology, like 0 is equal to 0. 3. Check if it imposes any conditions on the variables. Identities are important in mathematics because they allow us to transform expressions into equivalent forms, which can simplify calculations and reveal mathematical patterns. Let's look at some examples to understand this important distinction. Let's start with our first example. This is an expression that we need to verify whether it's an identity or not. On the left side, we have the product of three terms x plus 1, x minus 1, and a third term x to the fourth power plus x squared plus 1. On the right side, we have x to the sixth power minus 1. Let's expand the left side to see if it equals the right side for all values of x. First, let's multiply the first two terms x plus 1 times x minus 1. This gives us x squared minus 1. Then we multiply this result by the third term x to the fourth power plus x squared plus 1. When we distribute the multiplication, we get x to the sixth power plus x to the fourth power plus x squared minus x to the fourth power minus x squared minus 1. Simplifying by combining like terms, we get x to the sixth power minus 1, which is exactly what we have on the right side. Therefore, this equation is true for all values of x, making it an identity. Now, let's look at our second example. Here we have the equation 2x times x plus 3 equals 2x squared plus 30. Let's solve this equation step by step. First, let's distribute the left side. 2x times x plus 3 becomes 2x squared plus 6x. Now we have 2x squared plus 6x equals 2x squared plus 30. Subtracting 2x squared from both sides, 6x equals 30. Dividing both sides by 6x equals 5. Therefore, this equation is true only when x equals 5, which means it's a regular equation, not an identity. Let's look at our third example. Here we have the equation 2 times the quantity 3x minus 1 equals 6x minus 2. Let's solve this equation step by step. First, let's distribute on the left side. 2 times 3x minus 1 becomes 6x minus 2. Now we have 6x minus 2 equals 6x minus 2. Since the left side and right side are identical, this means the equation is true for all values of x. Let's verify this by moving all terms to one side. 6x minus 2 minus 6x plus 2 equals 0. This simplifies to 0 equals 0, which is always true. Therefore, this is an identity because it's true for all values of x. Let's summarize what we've learned about identities and equations. An identity is an equation that is true for all values of the variable. For example, our first expression, the product of x plus 1, x minus 1, and x to the fourth power plus x squared plus 1 equals x to the sixth power minus 1 for all values of x. Similarly, our third example, 2 times the quantity 3x minus 1 equals 6x minus 2, is also an identity. On the other hand, a regular equation is true only for specific values of the variable. In our second example, 2x times x plus 3 equals 2x squared plus 30 is only true when x equals 5. Welcome to this mathematical problem-solving video. Today, we'll determine the values of a, b, and c so that the given equation is an identity. Let's start by looking at our problem. We need to find values of a and b such that the following equation is an identity. First, let's expand the left-hand side of the equation to prepare for comparing coefficients. Now, we'll rearrange the terms on the left-hand side to match the format of the right-hand side, grouping by powers of x. For this equation to be an identity, the coefficients of each power of x on both sides must be equal. Let's write out these conditions. Let's now set up a system of equations by comparing the coefficients of like terms. Let's solve this system of equations. From the second equation, 2b equals negative 4, which means b equals negative 2. Now that we know b equals negative 2, we can substitute this into the first equation to solve for a. We have a minus b equals 1, and substituting b equals negative 2, we get a minus negative 2 equals 1. Finally, we can find c by substituting the values of a and b into the third equation. We have negative 2 times b plus a plus c equals 3. Substituting a equals negative 1 and b equals negative 2, we get negative 2 times negative 2 plus negative 1 plus c equals 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.